Yeah. So I have put up some material on the screen. So, and this is, as I said, this is what I want to make sure you understand today. And later we will do other stuff, but this much you should understand clearly. So first of all, let us make sure that everybody understands the notation and the concepts. So I have put, there are two columns here. On the left, I'm talking in matrix language. And on the right, I'm talking in the language of linear maps. Now, on the left, I have written down a set, which is the set of m cross n matrices with real entries. That means that it's an array of real numbers with m rows and n columns. And on the right-hand side, I have two vector spaces and the space of linear maps between them. So m cross n matrices correspond to linear maps. Okay. When I say correspond to, that means it's a bijection between a set on the left and a set on the right. And then we will find that these are not just merely sets, they are vector spaces. So this is actually isomorphism of vector spaces. This, so let me first say bijection of sets. And then below I write, so this is important. So let me write it in capitals. So bijection sets, isomorphism of vector spaces. Out here. So then in the last lecture, I was talking in terms of column matrices, mn cross 1. So these are column matrices. In other words, these are matrices with precisely one column. So there are m rows, n rows, and only one column. And so these are both spaces of column vectors. On the left, you have column vectors of length n, and on the right, you have column vectors of length m. And the correspondence is between m cross n matrices and linear maps between column vectors of length n and column vectors of length m. Okay. Now, so what about this wavy double arrow? What does that signify? That means that, see, earlier we have already encountered the vector space called Rn, which is the set consists of n tuples of real numbers. And if you look at column vectors of length n, that is also n tuples of real numbers, except when I think of it as Rn, I think of it as an n tuple, and usually it's written as a row of real numbers with round brackets. And when I think of them as column vectors, I write them vertically. But it's just, in both cases, these are n tuples of real numbers, and the vector space structure is the same. So this is a isomorphism of one vector space, namely Rn with column vectors of length n. Okay, so they are, for all intents and purposes, the same, except they are described as different sets. But there is a bijection, and the bijection preserves the vector space structure. So that is what is summarized by the double wavy arrow. So the point is, in mathematics, one makes these identifications without explicitly mentioning it, and you should get used to it. Okay. For that matter, column vectors of length n and row vectors of length n are also naturally the same things, So so I can take Rn and put it in bijection with row vectors of length n, so these are all three are different versions of the same vector space. Now, I began describing how to associate. So in the last lecture, we went in this direction, and that caused some confusion. So I want to spend time on that. In the last lecture, I went this way. I looked at a linear map from M cross 1 to M cross 1 and associated M cross N matrix to it in the last lecture. And then we have really not, so this is all going to be done today. Okay. So this material is going to be done today. This is where we ended the last lecture. And already at this point, there was confusion, and I asked you to think about the matter and look at the notes. So I hope you have done that. But if there are questions already about that, I can answer them. So
excuse me, sir.
Yeah.
Sir, in the notes, like there was a line where you have defined, where you basically said that it's like for Vj, it is equal to summation over Aij into Vi prime, something like that. So, sir, in this, if you reverse the order, like instead of Aij, if you define Ji, that implies that it's like that is basically coming, that ordering is coming from definition of like matrix product, right?
Why am I defining the ordering like that? Why am I subbing over the first index rather than the second index, right? That's your question.
Yes, sir. So, like, and my question is it coming from matrix multiplication?
Well, did you peek ahead a little bit in the notes?
No, like till page 30 only.
No, if you look ahead in a little bit in the notes, this will be made clear. In the matrix multiplication, if you want the usual multiplication, so the key thing is, look here. If you want this correspondence to hold, then you have to define things the way I did. What does this correspondence mean? It means on the right hand side, I have composition of linear maps, and on the left hand side, I have matrix multiplication. So if you want this correspondence to hold, then you have to define the things the way I did. So let us do this today, and then it will be clear, hopefully. So this was Ripunjay, right?
Yes, sir.
Yeah, okay. So this is really a small, it is not a difficult point, but it's something that you have to keep straight at right from the very beginning. Otherwise, you'll get hopelessly confused as we go along. Okay, so, and everybody, please pay attention to this. This is a really, as I said, a small but important point. So let me now work through the red arrow on top. Is there any other question? Okay, I'm going to repeat how to associate a matrix to a linear map between column vectors. Okay. So recall. So everything here is, the order in which I write M and N is important. So if I am looking at an M cross N matrix, that means M rows and N columns, you should really think of it as a map from column vectors of length N to column vectors of length M, okay? So how do you do that? Well, A hat, A, I, G, yeah. A hat E I is equal to sigma A J I E J prime. So this was J equal to 1 to M. This is, so given A hat, this is how you get the matrix A from A hat. So note that the array of numbers A, J, I, the first index runs from 1 to M, and the second index runs from 1 to N, because here I runs from 1 to N. What is EI? EI is this vector 0, 0, 1 in the ith place, 0. So, and what is the length of this? The length, so E1 is 1, 0, 0, and En is 0, 0, 1. So there are n of these vectors which give a basis for M n cross 1. Then I have Ej prime, which is 0, 0, 1 in the jth place. And this is size M. So E1 prime is 1, 0, 0, 0, dot, 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 and EM prime is 0, 0, 0, 1. So this is a basis for M cross 1. Now, A hat maps this vector space to this vector space. So I can apply it to each of the basis elements, basis vectors of the basis of this basis. In particular, when I apply it to EI, I'll get a vector here, which can be written in terms of the prime basis with scalars. And these scalars determine the entries of the matrix A corresponding to the linear map A hat. That is the procedure by which I am associating a matrix to a linear map. So this already caused quite some confusion in the last lecture. So I want to make sure that everybody understands what we are doing. Ruptak, are you okay?
Yes, sir.
Yeah. Shakti? Chauhan?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Yeah. So now let us check various things. First, note the map A to A hat, sorry, A hat to A is linear. In other words, if I take A hat and another linear map A hat prime, and then look at the corresponding matrix, that will be A plus A prime. And then if I take a scalar lambda and multiply it by lambda, the linear map by A lambda, that will go to lambda times the matrix corresponding to A hat. So this map that associates a matrix to a linear map is actually a linear map between the vector space of matrices of size m cross n and the linear vector space consisting of linear maps from this vector space to this vector space. See, the maps from here to here. So in other words, this is what I began with. This is a vector space. This is a vector space. And this map from which going from here to here, A hat going to A, that is a linear map between the vector space of linear maps to the vector space of matrices. So A going to A hat is a linear map, i.e. from the, sorry, it's the other way, A hat going to A from the vector space linear maps m n cross 1 to m n cross 1. So this is one vector space to m cross n matrices. Now, note that this is an injective map. Why? Why? Well, so you have to say, suppose A is 0, is A hat 0. To say that a linear map from one vector space to another vector space is injective, all you have to do is to check that the kernel of the linear map consists of the zero matrix. Sorry, the zero vector. So in this case, the zero vector is a zero linear map. So when is the matrix? So look at this correspondence from, look at this, look at the way I defined the matrix AJI from starting from the linear map A hat. So if the AJI are 0, supposing the AJI are 0, what does that say about A hat? So, well, if AJI are 0 for every IJ, this implies that A hat acting on every EI is 0 for every I, which means that A hat acting on any vector V is 0 for every V. This implies that A hat is the zero linear map. So the claim is proved that if the matrix associated to a linear map is 0, then the linear map is itself 0. Okay. Now I claim that in fact this map is onto. In fact, this map is not only 1-1, which we just proved that the map is 1-1, but also onto. Now, we are going to prove that by actually giving a map the other way, which gives the inverse map. So if I have a 1-1 onto map of vector spaces, then it's an isomorphism, and there is an inverse map which will also be 1-1 and onto, and conversely. So to prove this, we show how to associate to every n cross n matrix a linear map A hat from n cross 1 to m cross 1 in such a way that, so this is the inverse of the earlier map. So earlier I showed you how to go from here to here, A. Now I'm saying that I'll give a way of going the other way. And in fact, the point is, if by doing this I ended up with a different linear map, then clearly something is wrong. But we'll show that in fact
Sir, you are muted.
Sir, I think you're still muted.
sorry, my iPad seems to have unilaterally stopped the broadcast. I will start it again, but I need to sign in again, so this will take a couple of minutes.
Recording in progress.
Yeah, sorry for the interruption. So now, how to associate a linear map from column vectors of length n to column vectors of length 1? Well, there is an obvious way to do it, namely, so A hat acting on a column vector of length m, length n, what should it be? So the data, this time you are not given the linear map, you are given the matrix. So how do I get a column vector of length m starting from a column vector of length n and an m cross n matrix?
Multiplication.
Well, multiply. So this is A, this is an m cross n matrix, and multiply the column vector of length n. So which is this is a n cross 1 matrix. So if this product will be m cross 1 matrix, because that is how matrix multiplication works. So now I've gone from matrices to linear map. A hat, that this is indeed the correct thing to do, because what is A hat V1 Vm Bn? This is A hat acting on sigma Vi Ei, I equal to 1 to n. I have just written the column vector of length n in terms of the basis vectors that we have already got. Remember, v1 to vn are scalars. v1 to vn are n real numbers. So this makes sense. This is just the scalar number vi multiplying the basis vector ei, which is a column vector. Now, because A hat is a linear map, this is sigma I equal to 1 to n, Vi A hat Ei, but this is I equal to 1 to n, Vi A Ji E J prime, which is sigma j equal to 1 to m. So what does this say? This says that this is equal to the following column vector of length m. I hope I have this. Okay, so this tells you exactly what was claimed here. Okay, this computation. Okay, Perhaps this is not entirely clear, but you can check it yourself. It's there in the notes. Okay. The indices are so designed so that this is true. Okay. Okay. So now let's go back to what was claimed here. Yeah. So now look at this fact, the fact in green. So this was claimed. The matrix product corresponds to composition of linear maps. So let us work through this carefully. And
Sir, just 1 second. Sir,
Yeah,
sir,
yeah,
could
1
you scroll up to the
I will do
above
that.
matrix?
I will do that. I'm just making sure that we are continue to record. Yeah. Yeah.
Sir, the summation should be like A11 V1 plus A21, right? I mean, when the J varies.
No. That is the whole point. Look here. Look here. You remember A hat EI was defined like this.
Yes, sir.
Okay. So now all I have done is interchange the order of summation J and I here. Going from the red, this here, from this step, just look at this. Look at the red step from this equation to this equation. This arrow here. Sorry, 1 second. Let me get my. So look at this equation, which relates. So what have I done here? I have interchanged the order of summation. That's all I have done.
Yes, sir. I see, sir. No, the
Yeah.
mistake. Yes, sir. I
Yeah.
missed
Now you
that
see
I
that
equal to
the
1.
summation is in the second index of AJI.
Okay, sir. I
Huh?
missed
And
that.
to get this right, you have to in this definition, in the first definition, here you need to have summation in the first index for this to happen. That is the whole reason. For those who are in fact, I say that, so if you look at the notes.
Yes, sir. It is written explicitly that
Yeah.
the sign. This.
Yeah.
Yes, sir.
Yeah. Okay. So in fact, since you asked this, okay, let me. So before I come to the claim, the green claim, so let's spend some more time on this. Yeah. So see, there are two equations that you have encountered. Okay. So one is that A hat EI equal to sigma AJI EJ prime. This is the first equation. So this defines A in terms of A hat and vice versa. Okay, so given the matrix, you have the linear map by this, and given the linear map, you have the matrix by this. So this is how you go between matrices and linear maps. But what are these guys? These are actually, this is an equality of vectors. In n cross 1. So both sides are vectors in m cross are column vectors of length m. Now you also have, if I look at, if I define v prime equal to a hat b, so this is a column vector of length n. This is a column vector of length n. This corresponds to, in matrix language, v hat prime is equal to a.
Sir, it should be of length m, the v at prime, the vector v prime.
On the right, no? Yeah. No, this should be length.
On the left, on the left, on the left.
On the left. Yeah, thank you. N to length n. Okay. So, but here, so this is matrix multiplication. And then in terms of the coordinates of these column vectors, you will get v prime I equal to a ij vj sum over j equal to 1 to n. Okay, so and this is an equation on both sides are real numbers here. So in other words, if you look at this equation, this is an equality of both sides are column vectors, and here both sides are real numbers. So, and note that in the second equation, the sum is over the second index, and in the first index, the sum is over the first index. I don't know if this helps. This also I have explained in the notes, so you can stare at it there. So see that the entries of the matrix figure in two different ways. One is when you have this equality of vectors, which you see on top, and the other is when you have an equality of real numbers, which you see here. I mean, of course, these are not arbitrary real numbers. These are coordinates of vectors in the two vector spaces. This is not difficult. I mean, it is largely a matter of bookkeeping, but you should get used to it. Okay, so now let me talk about composition of linear maps and products of matrices. Can I go on? I think you are still a little confused about this first index, second index business. It is right to be confused, but I have taken care about this, and he explained it in the notes. So if you spend some time with it, you will see why things have to be defined in this way. Very good. So let me just go on to the next topic, which is composition, which was the stuff in green. Okay. So I will not write down the full sentence. I will just write this DA. So on the left-hand side, I have composition of linear maps. And on the right-hand side, I have, actually, I think I do it in some other way. Let me just stick with the notes. 1 second. Yeah, okay. Okay, so supposing I start with so let's start from the left and work our way. So we will work our way this way. Okay. So I have M n cross 1, M cross 1, and then I have L cross 1. I can switch to black. Okay. So I have a linear map from here to here, and then I have a linear map from here to here. So I can first apply a hat. So what does the composition mean? B hat composed with a hat acting on a vector V. So this is in M cross 1. By definition of composition is B hat acting on A hat V. So I start with the vector here that when I hit it with A hat, I get a vector here. And then when I hit it with B, I get B hat acting on A hat V. So that defines, so this defines, so this is defined by this. Okay. And compositions of linear maps is linear. So I get a linear map from, so M n cross 1 to n cross 1 and L cross 1 A hat followed by B hat. That gives you B hat A hat from here to here. That's a composition. So the point is, so then I will have a matrix. I'll have a so corresponding to B hat A hat, we will have a matrix of what size? Of size. Okay, you have to answer. B hat A hat goes from column vectors of length n to column vectors of length 1. So what should be the size of the corresponding matrix?
L cross n.
It should be L cross n. Okay. On the other hand, I have A, which is of size M cross n, and B, which is of size L cross n. So how do I manufacture? How do I take this and manufacture a matrix of size L cross n? Clearly, I can take the product, matrix product. And that will give me a matrix of size L cross n. And it is not surprising that that is the matrix that corresponds to B hat A hat. So let's check that. Well, B hat A hat acting on EI is B hat acting on A hat EI, which is B hat sigma AJI EJ prime, which is by linearity of B hat sigma AJI B hat EJ prime. Now I haven't chosen a basis for L cross 1 matrices, but we can choose them in the same way, except I have to find a way of distinguishing the 3 vector spaces. So I'll put a double prime on this. So this will be sigma AJI BK D K D J. No. I'm following into the same trap. B K J E double prime K. So this is E double prime 1 to E double prime L is
But
a
the
basis.
summation is over J, right?
Summation over is first over J, and now there is an additional thing being summed over J and K.
Okay.
Okay. So now if you look at this, this is sum A, B, J, K, A, J, I, sum over J, and sum over J. This is the whole point. A, J, I. Sorry, 1 second. B, K, J. What have I done? And by definition, this is B composed with A, the corresponding matrix K, I. Okay, so we have indeed proved B hat A hat remove hat Ki is B Kj A Ji sum over J, which is B A Ki. So let me, I made a mess of this. So let me. So we have proved if I take the linear maps B A hat, hit it on the left with B hat, take the composition, look at the corresponding linear map, then remove the hat. So I will just say remove hat, because this is a linear map. So by remove hat, I mean look at the corresponding matrix, look at its Kith entry, that is sum over J Bki A Bkj Aj, which is the matrix product of B and A, its Kith entry. So in other words, now as matrices, the matrix corresponding to BA, B hat composed with A hat is the product of the matrices B and A. So once we have this, then if I look at three linear maps.
Excuse me, sir.
Yeah, so 1 second. Yeah.
Sir, like, didn't we prove that if V prime is A hat of V, then V prime is A into V, right?
Right.
Right. So can't we use that result directly?
We can use this to prove this. We can use that definitely. But this is I mean, you can certainly use that. Yeah. This is not in any case, this is, you see, again and again, I'd like to illustrate this, how the indices kind of sort of arrange themselves so that you get exactly what you expect. But you can use that also. Yeah. So, but the key thing is, regardless of how you verify this for yourself, what you must remember is this fact. Okay, that if I have linear maps from column vectors of length 10. Okay. Wait, okay, I don't want to just, yeah, is this fact?
Yes, sir.
Yeah. Composition of linear maps corresponds to multiplication of matrices. So now, a very well-known fact about compositions of maps, not just linear, is that compositions of maps is a associative operation. So for arbitrary maps of sets, so supposing I have a set X, a map G to Y, and another map F to Z, then if I look at this map, which is G composed with F, and then if I have an H, if I tag on an H here from some W, then I can go from W to Z in two ways. I can go like this and then like this, or I can go like this, H composed with G composed with F. Or I can do F composed with G composed with H, and these two are equal. Okay, so let me get rid of the mess of stuff below. So given four sets and three maps, H, G, and F, we have F composed with G composed with H is F composed with G composed with H. This follows from the definition. Okay, why? Because F composed with G composed with H, acting on a small element here, is by definition F composed with G acting on HW, which is F composed with G acting on HW, and F composed with G composed with HW is also, if you unpeel the onion, it'll be the same thing. This will be F composed with G composed with HW, which is F composed with D composed with HW. Okay, so we have this equality of maps that the composition, if I have three maps, then if I can compose the first two and then the third, or compose the second and third and then the first, and you get the same map. And this is true for arbitrary maps. In particular, this is true for linear maps. So if I have three maps, B, C, and A, then C composed with B composed with A is C composed with B composed with A. And in matrix language, this implies that the matrix product C, B, A is C, B, A. So in other words, matrix products are associative. And of course, this is something you can check directly because there is, it's an easy fact. But this is just a reflection of the fact that composition of linear maps is associative. Of composition of arbitrary maps is associative. Therefore, in particular, composition of linear maps is associative. Linear maps correspond to matrices. Linear maps between column vectors correspond to matrices. Therefore, matrix multiplication is associative.
Sir, if the vector space is X and Y are equal, then we can just
wait 1 second. I'm going to now stop the recording, and now we'll chat in a more relaxed fashion.